Welcome back to my favorite people, and thank you very much for watching this video. And this lecture, I'm going to go through stereochemistry of SN1, E1 chemical reaction. And we said in E1, SN1 chemical reaction, the first step is going to be, or the rate determinant step is to create a carbocation. Carbocation, it will have a trigonal planar geometry. So I go trigonal planar geometry for the carbocation. It means your carbon, the central carbon, the one that it has a positive charge, it will be flat and it will be attached to three groups. Call them whatever you want. And there is an empty orbital here. This empty orbital, it can be sensed by the nucleophile. So the nucleophile, it can reach it from the top or it can reach it from the bottom. And that's going to give us technically different configuration. Whether we like, if we add it from the top, for sure, the configuration is going to be different. It's going to be inverted versus when we add the nucleophile from the bottom. So we will have two possibilities. The first possibility, we will have inversion in configuration. Configuration, I don't know why I said it gone. In configuration. And the second one, we will have retention in configuration. Okay. And I'm gonna try to practice those two. And this is the molecule that we have. So and if we, let's say, if we add the nucleophile from back of the molecule, and then we might get this. So let's say we get carbon. So say we have carbon. I'm going to keep two of them inside the plane. So I have carbon. Say this one is inside the plane. Okay. I go this one there. Here it will be the methyl. And I'm going to put I'm going to put the nucleophile here. And let's say our nucleophile, we're going to decide to go with OH. Okay, so let's say our nucleophile is OH. And or not OH, actually we should go maybe with this say CH3OH. Okay, so we're gonna have methoxide technically attached there. And what else? And then we need to have the ethyl. And where do you put the ethyl? I'm gonna put the ethyl inside the plane. So ethyl, it will be here. Okay, this is one case. Or you can put the ethoxide, the methoxide, you can put it on the right side. So I'm going to switch position of them. So say second one, I go carbon is here. Let's put the methoxide here. It will be CH3. Then we will have the ethyl here. That means the propyl group is going to be there, and the methyl is going to be here. Okay, let's sign the configuration. This is going to be number 1. This is one, it will be number 2, and this one, it will be 3. So the rotation, it will be clockwise. That's going to be R. And here is 1. Ethyl, the propyl, it will be 2. So this one is 2, and ethyl, it will be 3. This time it will be counterclockwise, and that's going to be S. Remember, methyl, it will be the 4th priority, and in both cases, methyl was back of the molecule. So what did I get? I got R and S. What was configuration of the starting compound? The starting compound, that was 1, here 2, this one 3. And so methyl, it will be the 4th one. That's counterclockwise, so it's going to be S configuration. So we got inversion. The first one was, we got it R, and the second one we had the retention, and we got it S. Okay, so I got technically two products, and the difference between them is the like the configuration of the stereo center. Now, how much from each one I get? Am I gonna get 50-50 from each one? If that's the case, I should get a racemic product. Okay, so if they are 50-50, if they are 50 from R plus 50 from S, then I will get racemic mixture. What does it mean? It means no optical activity. I should not see any change with the direction of the polarized light. Okay, let's go after this one and try to answer it. Now, we said the first step when it comes to losing the halide or creating carbocation. So forgive me, the first step of E1 or SN1 chemical reaction is losing the halide group or to create a carbocation. Now, what will happen to the leaving group? Is it just simply going to get away and stay away from the carbocation? In reality, no. A reason for it, and bromide has a negative charge, and the carbon does have a positive charge. So carbon is looking for electron, and where we can find the extra electron, and we can find it on the bromide that has negative charge. So under any condition, you are gonna see some interaction between the leaving group and the carbocation. Okay, so there will be interaction between them. And what do we call it? This is ion. Okay, this type of interaction, we call it ion pair. Okay, so we got ion pairs, and we got two ions. Okay, two ions that's like one with positive, one with negative charges, and those two are not that terribly attached to each other, but there is interaction with them. Now introduce the nucleophile. And so next step, we're supposed to add the nucleophile and say nucleophile. Okay, and the question is, which side is more accessible? Okay, the nucleophile, it can reach from this side. Okay, so my nucleophile can reach it from there, or it can reach it from here. So I go again, nucleophile. Okay, and let's call this one 1 and call this one 2. If we reach it from the left side, from number one, we will have inversion. Okay, so we will have inversion. Okay, if we reach it from the right side or number 2, we will have retention. Okay, retention in configuration. Now, number 2 is less accessible. Why? Because the bromide still is going to be there. So the nucleophile is going to have a harder time to see the positive charge from the right side, okay, or from number 2. That means number 1, it will be more favored. So what does it mean? It means the one that's like it has inverted configuration, it will have higher percentage. Remember, here we said this one is S, so I'm going to say the percentage of the R is going to be higher than percentage of the S configuration. Okay, so that means we're going to have some excess from R. So like the observed rotation is not going to be really 100% zero. Okay, you will have some enantiomeric excess from one of this enantiomer, and R is going to be the one that we will have a higher percentage from it. Okay, that's when it comes to like in the stereochemistry of the SN1 or E1. Now, let's make the example a bit more complicated and say we have such a molecule. This molecule, it has a tertiary butyl group up and hydrogen is down. Here we have ethyl, and down here we have bromide. Okay, the bromide is down. Okay, so again, these two I can here, this two, I can say I have, let's see, I have 1, 2, 3. This one, it will be S configuration. If I look at it from that side, I get 1, 2. Yes, it's S configuration. And here we have 1, 2, 3. That's going to be our configuration. This is equal to, if you draw the molecule this way, you can say the tertiary butyl is pointing up. So this is going to be the tertiary butyl. It is attached to 3 carbons. And the ethyl also is pointing up. This is going to be the ethyl. And the bromide is down here. And hydrogen is there. Okay. So you can say this one is up. And that one also up. Okay. Now, let's treat them with, for example, H2O, and you say heat. And see what will happen. Okay, first step, this is going to happen. We will get an intermediate. Okay, an intermediate is going to be this. Ethyl will be inside the plane. We will have a carbocation there. And the next step, okay, don't forget to show the tertiary butyl. The tertiary butyl is here, is pointing up. So this one is up. Okay. And of course, hydrogen is going to be down. Okay. Now I have hydrogen here. And this carbon also I have hydrogens, and I have 2 hydrogens. So I'm going to say I have hydrogen here pointing down, and one is up. Okay. Now, when it comes to the nucleophile, let's say your nucleophile is such a molecule, CH3OH. Okay. When the nucleophile is trying to reach the carbocation, it can reach it from up or down. So this one is from up, and that one from down. Okay. When one is trying to reach it from the top, it will see the tertiary butyl groups. The tertiary butyl groups will have some steric effect. And remember, any tertiary butyl group on any tertiary group, you will have 3 carbons, and those carbons also attach to 3 hydrogens. So the steric effect is going to be dramatical. Again, if I draw it, here you have a carbon attached to 3 carbons, and each of this carbon is attached to 3 hydrogens. And yes, we do have ethyl group here. And so if you have, let's say, orbital there, that orbital, it will be covered by the tertiary butyl group. So it will be harder to reach it from the top. It's not impossible. Okay, it's not impossible. Remember, there is rotation around that bond. So that group all the time is changing direction. And so sometimes it's possible. It's possible to get it from the top. It's possible. But reaching from the bottom is more favored. Okay, it's more favored. And now what do I get? I get 2 products. If I reach it from up or here down, when we reach it from up, this is going to be the product that we will get. We will have tertiary butyl group up, and then the nucleophile will be added from the top. So let's say we get this CH3. Okay, tertiary butyl group is also up. That means hydrogen is down. What will happen to the ethyl? The ethyl, it will go down. Okay. And another product, it will be the same thing, except position of the ethyl and the nucleophile will be swapped. It will be swapped. So let's change these two. If we change these two, we get ethyl on the top, but this is going to be OCH3. Okay, the question is which one of them it will be favored. Okay, the one that happened from the bottom of the one that we got it through addition from bottom of the molecule. So this is going to be the major product. and that one it will be minor product. Okay, and what was the reason behind it? The reason behind it was we had a carbocation that on one side and of that face or carbocation, we had too much steric effect. So addition from the top was not favored, while addition from the bottom of the molecule will feel less steric effect. Remember, here you have only hydrogen. Also, the bottom you have only hydrogen. So if you reach it from the bottom of the molecule, you're going to see only 2 hydrogen. Well, if you reach it from up, you're going to see entire of this tertiary butyl. Of course, there is hydrogen, but hydrogen is not going to have much steric effect. But the tertiary will have huge steric effect. So tertiary will make the addition from the top less favored, and from the bottom it will be more favored because we have less steric effect. And in this case, we say we have stereo selectivity. So when do we get stereo selectivity? Whenever one side of the molecule will be preferred instead of other side of the molecule. Whenever one side of the molecule will be preferred over that side, and second side, we say we have stereo selectivity. And what's the reason behind it? Steric effect. Steric effect is the major reason for it. And before I stop this lecture, I want to show the the RNS for the product. So here we said the starting compound, we had R there. Okay, so R here, we did not change the R. Now this, the second, we're gonna get here 1. This is gonna be 2, and this one it will be 3, and this one it will be number 4. So 1, 2, 3. That's gonna be S. So we get S here, and so if you flip position of the ethyl with the methoxide, then the configuration is going to be R. So what's the relationship between the first product and the second product? First product is RN and RNS, or you can say SNR, SNR, and the second one is going to be RNR. One of the stereocenters did not flip and stayed as it is. And I'm talking about this stereocenter. So we are talking about diastereomer. These two are diastereomer. And this is the end of this lecture. And thank you very much.